Hello and good day. In algebra, we're covering CO7, going from scientific notation to standard form. It sounds like we're still in the review realm here, which is a good thing. But scientific notation, its purpose is to aid in writing very, very large numbers or very, very small numbers. For example, did you know that the Earth is approximately 491 billion feet from the sun? If you didn't, then you learned a fun fact today. Let's write that number again. 491 billion. And again, 491 billion. If you were writing an essay, you might have to write 491 billion, something like 491 billion times, right? And that can get kind of old, okay? Reading a scientific paper or an essay that's just full of giant numbers gets old in a hurry. So scientific notation is a way to kind of shorten this up a little bit. Does anybody know the mathematical concept behind scientific notation? Sounds like, Lisa, you've covered this before, but first of all, let's go back here. What would this number be in scientific notation? Thumper.
491 times 10 to the 9th power.
Okay, you're close. You're close. Daniel?
491 to the times 10 to the 11th.
Okay, so in scientific notation, this number will be written. I'm trying to find the best way to write it up here. I'll just put it up here at the top. 4.91 times 10 to the 11th power. Times 10 to the, what's that? I just put it up in the name. You can write it wherever you want to. I just didn't want to I wanted to write large enough so people could see, but small enough to fit someplace, and that's where I decided to do it. So, but 4.91 times 10 to the 11th power. When we multiply something by 10, what are we doing? Why is 3 times 10 30? Or why is 2.5 times 10 25? Elise?
You move the decimal spot over.
Right. The decimal point moves one place to the right every time we multiply by 10. And we recognize here that, this is a power, 10 to the 11th power. How many times are we multiplying 4.91 by 10? 11 times. Which is why, to get back to this original number, we're going to be moving the decimal to the right 11 times. Okay? 2 spots to get to the other side of the 1 here, and then 9 more to account for all those zeros. Now, the first suggestion for this in scientific notation was 491 times 10 to the 9th. Scientific notation does more than just get rid of all the zeros. It does do that, but the rule is you have to have one non-zero digit to the left of the decimal point, which is why we put it between the 4 and the 9, 1. Okay? And that's how we get 11 here. The 9 zeros, yes, but then 2 more move. That looks like an H. The 9 zeros, yes, but the 2 more movements to get between the 4 and the 9. So what scientific notation really is, it's writing very large or very small, because in science you deal with very large and very small values often. Very small values using powers of 10, which in essence is just moving the decimal point from left or to the right. So writing very large or very small values using powers of 10. Okay. So let's practice on some of the ones that we have listed here. It says rewrite in scientific notation 5,670,000. Okay, 5,607,000. Right now, our decimal point, I'm going to make this a little bit bigger, I think. We can go away.
Pen down.
Pen down. Ugh. Ugh. Struggle bus. Okay, there we go. So 5,670,000. Right now, our decimal point is at the end of the number, right? We don't actually write it, but it's there. So our goal is to move this 1, 2, 3, 4, all those zeros, but then 2 more times to get between the 5 and the 6, 7. So we got one non-zero digit to the left of it. We write all non-zero numbers after that, the 6 and the 7. And then since we moved it 6 times, times 10 to the 6th power. Okay, yes?
Is the 10 always going to be there, like times 10?
Yes. This part, this times 10, will always be a part of it. Yep. And this is one of those few situations where we actually do use the X to show that we are multiplying. True scientific notation doesn't use the dot or the parentheses. It does have that X there. Okay. 878 trillion. My goodness. So commas are kind of helpful here because you can think of it in jumps of 3, rather than writing all the individual jumps, we can just kind of go, this is 3, there's 6, 9, 12, right? And then 2 more so that we have one non-zero digit to the left of that decimal. So 8.78 times 10 total, we move the decimal 14 places. 14 places. Yes, Bridget.
So the moving of the decimal is just helping you see what the times 10 to the power is?
Yes, because if I give this number to you in scientific notation, what this means is that from here, 8.78, you will move the decimal 14 places to the right to get back to our original number. Okay? It does. That's good. Soybean. I use the commas because I know every time that there's a comma, that's a group of 3 zeros, right? And so it's a group of 3 decimal point movements. You could just as easily draw, or show each individual jump. 1, 2, 3, 4, 5, 6, 7, 8, right? That kind of gets a little bit, I don't know, cluttered. So, but it's up to you. Yes.
Can we do the next one?
Yes.
Yeah.
Sounds like a plan. So the next one now, we're dealing with a very small number, aren't we? 0.00013. Our goal is still to write this so that there's one non-zero digit to the left of the decimal. So we're still going to get that 1.3. But this time, because our number is very small, which direction do we have to move the decimal to get back to 0.00013? Well, we move it to the right to get between the 1 and the 3, but to get back to our original number from 1.3, which direction do we have to move it? Left. And when you move the decimal to the left, instead of being like multiplying by 10, that is divided by 10, so our exponent's negative. So it'll be -4. 10 to the -4th. Because how many times did we move it to get between the 1 and the 3? 1, 2, 3, 4. So to get back to that original number from 1.3 times 10 to the -4th, we have to move it 4 to the left. Okay? The last one, also a very small number. We're going to move this decimal 1, 2, 3, 4, 5, 6, 7 times so that it lands between the 4 and the 9. The reason why it's between the 4 and the 9 is we need that one non-zero digit to the left of the decimal. And I already forgot how many times we moved it. Was it 7? 7. So 4.901 times 10 to the -7th. -7th. So in the first two examples, we kind of separate these between a positive power here and a negative power. Why is the exponent positive in those first two? There are two reasons why the exponent positive, what a positive exponent tells you. Yeah.
Because to move the decimal backwards, it has to be positive, and to move it forward like this way, it needs to be negative.
So it has to do with what you're doing to get back to the original number, right? Because in these first two examples, the numbers are very big, okay? The values are very large. From 5.67, you have to move the decimal to the right to get back to 5,670,000. So the exponent is positive because it moves right to get to the original number. We are multiplying by 10. A positive power means the value is very big, okay? And it'll move to the right to get back to the original number. A negative exponent means your value is very small, okay? Small value. And because it moves to the left, we're dividing by 10 to get back to the original number. Back to original number. Okay? Good so far? Light bulbs from last year flickering on? Remember this? The next section goes over rewriting the values in standard form. So it's going from scientific notation back to standard form. So we have 7.613 times 10 to the fourth. 7.613 times 10 to the fourth. Which direction am I going to be moving this decimal point to get back to the original number? Are we going to be multiplying by 10 4 times or dividing by 10 4 times? Soybe. We're multiplying. That positive power tells me this number is going to be big. Okay? And so multiply by 10 once, twice, 3 times, 4 times. That extra hop, that extra jump gets filled in with a 0. And so our original number was 76,130. All right? 6.8 times 10 to the 10th. Which direction? And how many times? Lucas?
To the right 10 times.
To the right 10 times. Okay, positive power. We're multiplying by 10. We're going to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's kind of helpful. I mean, it takes one hop to get to the other side of 8, and we got 9 hops left. All those hops will just become zeros. So our number is going to be 6, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. 68 billion. Whew. All right. 5.1973 times 10 to the negative 7. Which direction and how far? Exponent negative means we're going to the left 7 times. So 1, and then 1, 2, 3, 4, 5, 6 more. Our decimal is now there. All those jumps get filled in with zeros. And then since it's a decimal, we have 0 holes out in front as well. So 0.00000051973. Okay. And the last one, power of negative 2, 2 hops to the left, 0.0821. Questions on any of that? It's pay attention to the sign of that power, right? Positive to the right, negative to the left. The second page is all practice that you get to do when scientific notation, going both from standard form to scientific notation and from scientific notation to standard form. The question at the bottom, we have our first introduction, I believe, of our little nifty fun fact guy down here. At the time of this document's last edit, I was about 1.33 times 10 to the 9th seconds old. How many days is that? Quite a few is correct, but I need more specific. Yes, Kylie.
I have a question about the ones where they don't give you a decimal, they just give you like numbers.
So maybe like this one? Okay. Let's take the 18 million there. What's your question about that? So this is the original number, right? So when we write the number in scientific notation, what two numbers will our decimal be between? 1 and 8. Okay. So if you know that much, then the question becomes, well, how many times do we have to move it to get there? And when you're dealing with a number that's greater than 0 here, right? It's big. Our decimal isn't written because it's at the end of it. So then from that point, and you can use the commas to help you or just do the individual jumps, we have to move it 1, 2, 3, 4, 5, 6, 7 times. So that's where we get 1.8 times 10 to the 7th. The power is positive because to get back to the original number, we have to multiply by 10 7 times. Yep. Any others on these you want to talk about that look? Yeah, Quinn.
Can we do the last question? Like
The fun fact question. All I'm going to say for that one is, using scientific notation, you can calculate how many seconds old that represents, right? And then you need to convert that number of seconds to days. So you have to think, well, how many seconds are in an hour? How many hours in a day? So there's some conversion stuff there. What's that? Round up? Depends on what the decimal is. If it ends up being like, well, don't share with everybody. Let everybody experience the experience, I guess.
the experience of brain.
Yeah. Round up is fine. Round up, round down is fine. So this gives you the number of seconds. I want the number of days. So there is some conversion that needs to happen there. Any other questions on the homework? This is due tomorrow. The rest of CO7, yes. Well, how many seconds are in a minute? Then how many minutes in an hour? How many hours in a day? Yeah, nope, not 12. All right, folks, thanks very much. You were excellent today. That is how you math.